All right, hello again, everybody. Welcome back to MTED 110. Today we're going to be finishing Chapter 9. This is Lecture 9B. Let me go ahead and pull up the slides and we will get started. All right, so we left off here, Activity 9A. We're going to start with this, and I'm assuming everybody knows this at this point, but a percent is just a ratio in which the denominator is 100. And what I'm going to do here is throw up some quick problems to try. So what I want you to do is I want you at home to try to solve these problems mentally, okay? So try to solve them mentally. Go for it. Okay, now let's try to talk about what we did mentally, all right? And again, you should try to talk this out with your group members as well while you're sitting there doing that thinking, right? So first, let's do this. Let's read the first one. It says 30 is what percent of 45? Okay, so what this is asking is the number 30 is some percent of 45, and we want to know what it is. So how could we do this mentally? Well, okay, first off, let's see. It's going to be more than 50% because half of 45, which is 50%, that's 22.5. So it's got to be bigger than a half. But this is about where you might recognize that there's a really nice common factor. In fact, the greatest common factor is 15. So 30 is 2 15s and 45 is 3 15s. So that means that 30 has got to be 2/3 of 45. And if it's 2/3 of 45, that means it's 66.6 repeating percent. Let me draw a little picture of that actually. So if we know, once we realize that 15 is a common divisor, we can do this right here. 15, 15, 15. I'll even do this up at the top here. This is 45. Now 30%, I'm sorry, 30 is this quantity right here. So if you look at just the parts, we can see that it's 2/3. 2/3 right there. So 2/3 of 45 is 30, or 30 is 2/3 of 45. Now, 2/3 is 0.6 repeating. That's something we actually saw in the previous chapter, but you might not remember it. This is one of those ones that you should probably memorize, that 2/3 is 0.6 repeating. And that means that it's going to be 66.6 repeating percent. So that's how we could do that one. All right, what about number 2? Number 2 says, what number is 50% of 60? Well, that one's not too bad, right? What number is half of 60? The answer is 30. What about number 3? Number 3 says 16 is 25% of what number? So 16 is 25% of what number? That means that there's some bigger number that 16 is 25% of. Well, 25% is just a quarter. So what we're really saying is that 16 is a quarter of this number that we're looking for. So if we had 4 of those, then we would know what the number is. So let's just count. 16, 32, 48, 64. So that's it. The answer is 64. Notice that I was just passing between fractions and decimals and parts willy-nilly, right? That's why we spent so much time on that stuff before. All right, now let's look at the last one. Number 4 is a little bit trickier. It says 25 is what percent of 40? 25 is what percent of 40? This one's a little trickier because it's not immediate like number 2 was, or even number 3 to some degree, right? The numbers aren't as nice. But we can use our number sense and we can use benchmarks to help us here. So for example, I know that 20 is 50%. 20 is 50% of 40. And I know that 30 is going to be 75%. Let me write that out actually, just so we don't get too lost. What I'm saying here is that 20 is 50% of 40, and 30 is 75% of 40, right? Because it's like quarters again, right? It's like 10 is a quarter of 40, 20 is a half, 30 is 3/4, and 40 is the whole, right? Okay, but here's the thing. 25% lies right in between these two. So 25%, or sorry, what am I saying, 25%? 20, Wait, where did it's 50? Oh yeah, sorry, I'm looking at the wrong problem. Here we go. That one down there. So 25 lies right between those two. So the percent we're looking at is the percent that's directly between 50 and 75, equally spaced, you could say. Well, that's going to be what? It's 15 divided by 2. So it's going to be, what is it? 15 divided by 2. Let's see. What is that? 6.7 point. It's going to be 67.5%. Is that right? Well, 7.5 plus 7.5 is 15. So that's right. There we go. So we can do that type of reasoning in our head, right? We just have to think about those benchmarks and the sizes of these numbers, right? And actually, we can use pictures too. So this is the picture. Oh, wait, 62.5. What did I do wrong? Oh, no. Let's go back and see. I said 67.5. What am I thinking? Oh, you know what it is? You know what it is? It's not 15 apart, they're 25. Look. The difference between these two is 25%. So I need to add 12.5%. My bad. My bad. So this should be a 12. There you go. 62.5%. 62.5%. See, this is why we got to work in groups, right? Because if you're working in a group, somebody will catch that. Luckily, I had a little note for myself. There we go. Anyway, but that's the idea. So the process still works. And then these are the other pictures for the other problems too, if you want to take a look at those. That's the idea. Okay, so this is one of the reasons why understanding percents and having this type of mathematical skill is important, because it's going to help you out in the real world. So let's do this. Your boss says, hey, remember when business was bad last year and I had to cut everyone's pay by 10%? Well, business is much better now, so I can raise your pay by 10%, and that'll put you right back to where you were before the cut. Is your boss correct? Or is he lying to you? Think about it for a minute. What do you think? All right, let's talk about this one. In this case, he is not correct. He's not correct, and he is lying to you. Whether that's malicious or just ignorance, who knows, right? Depends on the boss, I suppose. But the idea is this. So what happened was last year, the boss cut everyone's pay by 10%. So that means that whatever pay everyone was getting, they're getting 90% of it now. So let me go ahead and, you know what, for this, I'm just going to use some variables just for our own edification to make it clear. It'll be a little clearer why this works for us. But we're going to do this. We're going to say let X be our original wage. Then 0.9x is our wage after the cut, right? So remember, 0.9 is 90%. 90% is 10% less than 100, so that reflects what our new wage is going to be after the cut. All right, so now what he's saying is, hey, if I increase your current wage by 10%, it'll put you right back to where you were. So what he's saying is this. He's saying, I'll give you your current wage, which is now 0.9x, and I'll add on to that 10% of that amount, which is 0.1 times 0.9x. And what he's saying is that that's going to put us right back to where we started. It's going to put us right back at 100% x, right? Is that true? What do you think? No, that's not going to be true. That's not going to be true. And it has to do with the fact that this is going on. It's not doing 10% of our original wage. He's doing 10% of our reduced wage, which is going to be smaller. So he's trying to pull a fast one on us, right? At least I think. Or maybe he just has no idea how to do this type of math, which would not be too surprising. I actually had a boss tell me essentially that he couldn't do math. When I was working in plastic fabrication, and my boss was telling me how he got a degree in communications, and he said he tried to minor in business, but the algebra was too hard. So that was my boss. Yay! So needless to say, I didn't trust his math very much. Luckily, I don't think he did much of the math. I think his wife did most of the math now that I think about it. Anyway, so you got to know this type of stuff so you can, got to keep on your feet and protect yourself and advocate for yourself. You need math. All right. Okay, how about this one? So this one is great. If you haven't, I feel like everybody needs to experience retail work at least one point, at least one point in your life. So if you've never had to be like a clerk or somebody who works at a register or had to work retail or deal with customers, you really, really should. And this is one of the common arguments that comes up between customers and clerks. So let's take a look at this and see if we can make sense. You buy an article of clothing, say, and it's on sale for 20% off the original sales price. And you're doing this in a city where there's an 8% sales tax. The clerk calculates the total with tax and then applies the discount. The question is, were you cheated? And if you were cheated, by how much? So think about it for a minute. Were you cheated? Because what the person's doing is they're applying the tax and then the discount. They're not applying the discount and then the tax. So were you cheated? Hmm. Okay, let's think about this. We should be able to determine one way or the other, right? So let's see if we can do it mathematically. Let's see. So total with tax. So if we're going to calculate the total with tax, then what we're going to do is we're going to pay the original price plus 8% of the original price. So this is what we get right here. I'm going to let X be the original price again. Let X be the original price. Then X plus 0.08X, and that's actually equal to, actually, you know what, let me put that down here. Let me put that down here. Ah. Which is equal to 1.08x. If you distribute, or actually if you factor, right? If you factor this out and factor that out, you'll get 1.08 times x. That's the idea. So then this right here is the price after tax. Then that is the price after tax. Handwriting is awful on this thing. After tax. The pencil is a little bit too slippery for me. I need some grit, like when you write on a piece of paper, right? I've been trying to figure that out, but I can't find anything that'll work. Okay, so 1.08 is the price after tax. Now we're going to apply the 20% discount. And if we apply 20% discount, then what that means is we're only going to pay 80% of the price that's listed right there, right? That makes sense. 20% discount means you pay 80%. So we're going to end up paying 0.8 times 1.08x. And that's the final price. Okay, so my question is this. Is it going to be different if we first apply the discount and then the tax? Well, let's find out. I'm actually going to save this up here at the top, give myself some space. We'll put that right there. Okay, now let's go through and do the other one. So let's keep X as the original price. But now what we're going to do is we're going to apply the discount first. So once we apply the discount first, this will be the new price. So that's the original price after the discount has been applied. Now what we're going to do is we're going to apply the 8% tax to that. So that means we're going to pay this price plus 8% of that price. And so what you're going to end up with is exactly the same situation we had before, where we had this times 1.08, right? There we go. So now my question is this: is this quantity different from this quantity? What do you think? No, those are the same. Those are actually equal. Those are equal. That's the same quantity. And why is that? Because multiplication commutes, and we saw why. We actually saw a visual representation of why that's the same quantity. But that's what it is. It's the same amount. So it doesn't matter if the clerk applies the 20% discount before or after tax, the price will still be the same, right? So now you can explain it to the customer, and then they'll be like, oh, okay, that makes sense. And then the next customer will come up and ask you the same question, right? That's how it goes. Okay. Let's do a third one. Ah, so look at this question. This one says, you buy an article on sale for $20 off in a city where there's an 8% sales tax. The clerk calculates the total with tax and then applies the discount. Were you cheated now? Hmm, think about it. These questions are virtually identical. There's only one thing that's different about them, except the very last line. But there's only one thing that's different about them. Can you see it? Hmm. Hmm. You see the difference? It's right there. There's the difference right there. In the first one, it was a 20% discount. In the third one, it's a $20 discount. That's actually a very important distinction because this is a multiplicative discount and this is an additive discount. And so tax is multiplicative. Tax is applied multiplicatively. So if you do a multiplicative discount, or if you do a multiplicative tax and then an additive discount, that's not the same as doing an additive discount and then a multiplicative tax on top of that, right? So it is actually different. And in this case, I think you will be cheated, but I'm going to leave that for you to try at home. So see if you can calculate, or see if you can show, just like we did back here, that those two things, in fact, are not going to be equal if you do them in two different ways. Try it out on your own at home, okay? All right. Oh, yes. Okay. Yay. I've been so excited about this. I've been excited about this example for like, like three whole lectures. This is like a legit, real problem that I had to solve in life. And I was so excited when I had to solve it because I was like, this is exactly what MTED is all about. MTED 110. We learn about this and I had to use these skills. So here it is. Mr. Richardson needs to make a spray cleaner that's part bleach and part water. Now, Target's Up and Up brand says to use 1/3 a cup of bleach per 2 quarts of water. And they say to do that in order to do this, in order to create a mixture suitable for disinfecting kitchens, dishes, and sinks. Now, this is actual, like the actual jug. So if you like go to Target and you look at that, their like generic jug of bleach, it'll have these on the back, right? So it also says this. It also says to use 1 cup of bleach per 1.5 gallons of water if you want to create a mixture suitable for disinfecting and deodorizing bathrooms. Well, I mean, I needed to do both, right? I need to disinfect my bathroom and my kitchen and everything, right? COVID-19 everywhere. We got to be clean, right? So, what I needed to do is I needed to figure out which one was stronger. Which mix is a stronger mix, right? So, which is the strongest? Think about it for a minute. Think about it and see if you could work it out. Okay? Now try to write some things down. See if you can calculate it yourself. All right, so let's do this one together. I was really excited when I saw this because I was like, oh, I can do this. I can do this. So let's look at the first ratio. Let's look at let's look at the first ratio, the one that's suitable for kitchens, right? And what it says here is 1/3 of a cup of bleach per 2 quarts of water. So it says 1/3, actually, I'll use black here. 1/3 of a cup to 2 quarts, right? And I was like, okay, well, what's the unit fraction? How much do I need for 1 quart? 2 quarts. What is this 2 quarts? How much do I need for 1 quart? 1/6 per one. There you go. And that's just finding the unit fraction. So this is much more handy for me because I know that I need 1/6 of a cup of bleach for every 1 quart of water. And then I was like, okay, let's do the same thing for the second ratio. The second ratio says 1 cup of bleach to 1.5 gallons of water. And I was like, okay, well, let's find a unit ratio. And I was like, okay, this is actually 1 to 3 halves. So that's the same thing as, sorry, 2/3 to 1 gallon. So the important thing here to recognize is that the units are not the same, quarts and gallons, right? But check it out. It says 2/3 of a cup per 1 gallon. And we know that it's 1/6 of a cup per 1 quart. So what I really need to do is I just need to find how many quarts are in a gallon. And luckily, we can tell that pretty easily. That's four. There are 4 quarts in a gallon. Why is that? Because that's why they're called quarts. They're called quarts because there's 4 quarters in a gallon, and each one of those is 1/4 of a gallon. That's the idea. Same thing with a fifth. If you've ever heard of a fifth, It's a fifth of a gallon. So that's what it is. So we know that there are 4 quarts in a gallon. So all I need to do is convert this measurement to be in terms of gallons, or in other words, 4 quarts. So what I'm going to do is bring this down here, and I'm just going to multiply the top and the bottom of that ratio by 4. So I'm not changing anything, right? I'm not changing anything. And I'm going to end up with 4/6 to 4. So that's 4/6 of a cup to 4 quarts, right? But here's the beautiful part. 4/6 reduces to 2/3, and 4 quarts is the same as 1 gallon. So this is saying that the ratio from the first one, the one that's suitable for kitchens, is 2/3 of a cup per 1 gallon. And lo and behold, they're equal. They're equal. They're the exact same ratio. They're the exact same ratio, which is hilarious. So it's not that one is more suitable than the other. It's literally they just took the same ratio and wrote it in 2 different ways. Why did they do that? Well, I figured it's because people tend to make less cleaner when they're trying to disinfect their kitchen and lots of cleaner when they're trying to disinfect their bathroom. And so they wanted to make that easier for people, I suppose. But frankly, I feel like it would be a lot easier just to say this: 2/3 of a cup to 1 gallon. That'd be so much easier because it's a unit ratio. It's a unit ratio. Notice that I didn't start trying to do like cross multiplication and like setting up a proportion. In fact, in this case, doing it that way would be way, way harder. It would be way harder. It'd be harder because then you have to include this conversion process right here. Yeah, you have to include that conversion process somewhere. Where and when? It's too hard, right? Unit ratios, man. Unit ratios. All right. See, here we go. This is great. So this is from the Smarter Balanced exam, grade 8. So these are students that will be exiting middle school very soon and entering high school. And this is a great problem to give them because high school is like the first time when you can actually hold a job and get paid, right? You get your first paycheck kind of thing. So check this out. It says that George's weekly pay rate is $4.55 per week, and he receives a 20% raise. Yay! Awesome, right? So how can George calculate his new weekly wage rate? How can he do it? And then notice the problem actually says that what you have to do is you have to drag all of these different selections and like put them in the right, put them in the right box. So it's not just saying calculate it, it's saying which of these 6 different ways of calculating it would actually work to give you the new wage rate. Wow, see, that's very comprehensive. Let's see if we can make sense of it ourselves. We did something like this before, actually. Okay, so if we're making 455 per week and we get a 20% raise, that means that our new wage is going to be our original wage plus 20%. So another way of saying that is that it's going to be 455 times 1.2, because that'll be the entire wage, 455 plus 20%. That's this thing, 455, 1 plus 0.2. And there's chapter 2 coming back on us again, right? Splitting things up in terms of ones and tenths. And then we can distribute. And we're going to get 455 plus 0.2 times 455. There it is. Okay, so now what we can do is we can go through and figure out if any of these make sense. Let's start with this one. Would we get the new wage rate if we divided 455 by 0.2? Divided 455 by 0.2, what? Does that equal that? No, that does not equal that. It definitely does not equal that. So that one does not find the new wage rate. That one's definitely a no. Okay, next. What about this one? If we divide 455 by 1.2, wait, you mean this? No, that's not going to work either. Look, these are not equal. Division is not the same as multiplication, right? We're saying the correct answer is 455 times 1.2. That's not the same as 455 divided by 1.2. So that's a no. That one also goes no. And then you can kind of go through and see, right? Like we actually know this one is correct. So this one down here goes there. And then I'll let you think about the rest. Ponder those for a minute and see if you can figure out if those should go, or figure out which box those should go in. Just think about it for a minute. All right, what's next here? Oh yeah, okay, so this is where I need to give you a word of warning that it's common for phrases involving percents to be misinterpreted and also misrepresented. And this is kind of my like another one of those times where I have to caution you against misinformation and people abusing mathematics to tell you falsities. So let's talk carefully about this here. This is an example. This is a correct example. 25% larger than 1200 is correctly interpreted to mean 1500. And the reason is because what you're saying when you use this phrase, larger than, you're saying find 25% of that number and add it on to that number. That's 25% larger than, right? And that's why you get 1500, because 300 is 25% of 1200, and we're going to add that on. Now, compare that to this phrase, as large as. As large as is different. As large as means that you're going to be 25% as large as 1200. So you're not even going to be a whole 1200, right? You're only going to be 300 in the end, and that's correct. Still correct, actually. That's correct. But it's going to be a lot smaller, right? So this is how it works. As large as means direct multiplication. Larger than means you're going to have to add that on at the end, all right? So this is actually correct. This is how you would use it correctly. People tend to get confused when those percentages are larger than 100. So for example, saying 300% larger than, actually I'll keep the colors consistent, 300% larger than 1200 and 300% as large as 1200, they're often incorrectly interpreted to mean the same thing, or they're presented as meaning the same thing, but they're not the same. They're not the same at all. Let's compute it right here. 300% larger than 1200, that means you're going to find 300% of 1200 and add that on top, and pat that on top, right? So what's 300% of 1200? Well, 100% is 1200, so 3 of those is 3600. Oops. 3600 is 300% larger than 1200. Now, 300% as large as 1200 means you're going to take 1200 and multiply it by 300%. So what do you get? So, oh wait, I'm sorry, I just totally messed this up. Back up. Larger than, not 3600, 4800. There you go. Almost did it myself, right? That's why you got to watch out for these things. Wait, do you mean as large as, or you mean larger than? So larger than means this. You have to include, actually, let me stay consistent with the colors. You have to add this 300% on top of what you already got. That's what it means to be larger, 300% larger. Start with what you've got and then add 300% of that on top. But if you say something like as large as, that's where this is correct. 3600 is 300% as large as 1200. There we go. What's a number that's 300% as large as 1200? 3600. Because if you take 1200 and multiply it by 300%, you get 3600. So those are not the same, right? Notice that that's a different amount. It's not 4800. It's not 4800 in this case. So down here, or up there, you got 4800, but down here, you got 3600 instead. Okay. Oh yeah, so you can also use pictures to help with this. You can use drawings or strip diagrams. This is actually for the first problem up here, this one. So those are connected there. Here's the bar representing 1200. This is 25% larger. And then down here, this is 25% as large as. You're not even going to have the full 100%. You're only going to have 25%. Okay. So some things that I'd said before and some issues for learning, just to wrap this up. Research showed that even when 11 and 12-year-olds are taught the cross multiplication method, they often become confused and unsuccessful in using it. That's because it's a confusing process and you completely divorce yourself from intuition when you do it. It's a trick, right? Cross multiplication is just an algebraic trick. There's no like fantastical, like deep reasoning behind it. It's just combining two algebraic steps. That's really all it is. They avoid it. Students don't want to use that. You might use it now because it was ground into you for years and years. Cross multiply, cross multiply, cross multiply. And it's fine, you can use it, but you got to admit that you don't carry nearly as much intuition. Students tend to prefer the unit fraction method. And let's explain why with this problem. So consider this. John purchased 24 loaves of bread to sell in his grocery store last week at a total price of $26. If he wishes to buy 30 loaves next week, how much will he spend? That's the idea. So what this is saying is, if 24 loaves cost you 26, how much are 30 going to cost you? So a typical student response is this. This is typically how students respond. They'll say, if John paid $26 for 24 leaves, this means he must have been paying a little bit over $1 for each loaf. There's that estimation, right? He's paying a little bit over $1. $26 for 24, a little bit over $1. The exact amount is the ratio. The exact amount is 26 divided by 24, which is 13/12. So if John wants to buy 30 loaves next week, that means he just needs to pay 30 times that unit ratio, which comes out to 32.50. So that's why students prefer the unit ratio method, because it's basically saying, how much does one cost? And once you know how much one costs, you just multiply that by how many you need. That's all it is. All right. Okay, so Dr. Susan Lamman, a math education researcher, she investigated proportional thinking for many years, and she found the following characteristics of proportional thinkers. This is the type of stuff we want to instill in our students. All right, first, they can think both in terms of unit rates and multiple units. Two, they tend to be efficient problem solvers. They know how to play with these numbers and these ratios. That's the idea. Where is it? 24, 4 times 5, 15, right? So they didn't have to actually find the unit ratio here, but they could have. They can use partitioning to help. So for example, if 3 people share 5 pizzas, then each person gets 5/3 pizzas. Why is that? Well, each person gets 1/3 of the total 5. So 1/3 of 5 is 5/3. That's how much they get, right? So yeah, so there you go. They can think flexibly about quantities, and they can find unit quantities. So for example, if cans of spinach are 3 for 99 cents, then 1 is 33 cents. They're not afraid of fractions and decimals, and they can think flexibly with these representations, passing in between percents, decimals, fractions. There's no fear there. And the way that they get to that point is through us, the teachers. We're the ones who help them feel comfortable with it by helping them get over their anxiety of not knowing the answer right away. Totally fine. Nobody ever knows the answer, right? Nobody ever knows the answer right away. Don't expect your students to either. Help them go through that feeling of anxiety, and they can cope with it and they can overcome it. And then they won't be afraid. They won't be afraid. They can mentally compute with fractions. So this is an important thing too. And decimals and percents. For example, they know they can find 3/5 of a quantity if they know 1/5. And this is something we talked about in chapter 6, I think, chapter 6. And if they, and they can find 70% if they know 10%. That I know we talked about in chapter 7, I believe. I think it was chapter 7. Anyway, they can solve both missing value problems and comparison problems by reasoning about them, not just rotely using cross multiplication, right? And that's it. All right, so that's it for chapter 9. Let's take a look at activity 9B. All right, where are we? Let me pull this up here. Here we go. So 9B is mostly about percents. Yeah, so just kind of finding some percentages here. This one's pretty short. That's really all it is. So just computing some percentages. I think it won't be too bad for you. All right, well then I'm going to go ahead and call that a day. All right, thanks again for listening, and I'll see you next time for lecture 10A, and I'll see you at the collaboration meetings. Have a good one.